So let's evaluate combinations using. I guess we did this in part one already, no? And what we learned from part one is that we can solve combinations by checking out the Pascal's triangle. So right, for example, when we evaluate A3, that means we look at row 8 and check out diagonal 3, and where they intersect is the answer. So we did that. So letter D, you might be confused by this notation, 12C10, but that's just equivalent to 12 choose 10, or like 12 choose 10 is equivalent to 12C10 is equivalent to 1210. And if you use the formula, that's 12 factorial over r factorial, which is 10 factorial. And 12 minus 10 is 2 factorial. And so if you use that formula, we should get 66. But again, no, this emphasizes that we use the Pascal's triangle. We can use the Pascal's triangle as well to look at the 12th row and the 10th diagonal and where they intersect. So if we check that, the 12th row, and the 10th diagonal, we can choose this actually, the left diagonal. They intersect at 66. But if you also check out the right diagonal, they also intersect at 66. So I guess if you have a Pascal's triangle handy, you can easily answer combinations. But again, the formula I believe is easier in general. So now let's proceed to counting with the binomial theorem. So what is the binomial theorem? This is the binomial theorem. A plus b to the n is equal to n0, that's the first combination, n1, n2, dot, n plus n minus 1, n to the n. This is just where nr is the number in the nth row, rth diagonal of Pascal's triangle. So this binomial theorem tells us that the coefficients, if we expand our binomial, the coefficients are just members of the Pascal's triangle. So, and we established that the members or the elements or the numbers in the Pascal's triangle are actually combinations, diba? Like the first element is 0, choose 0. And in the first row, we have 1, choose 0, and 1, choose 1. So let's look at an example. For example, we have a plus b cubed, a plus b squared. Let's start with squared, right? So a plus b squared, we know that's a squared plus 2ab plus b squared. We memorize this, right? But if we use the binomial theorem, what we first do is write down the first element of the second row in Pascal's triangle, that is 0, 2 choose 0. And then we write a squared. We leave out b, but b will present itself later, second. And then we write the second member in the second row, 2, 1. And then we write a. So a squared pa siya din, nahimo na siyang a. And then b appears. And then we write the third element in the second row of the Pascal's triangle. So a disappears, starts with a squared, naging a to the 1, and then a to the 0, which is 1. And for b, it starts with b to the 0, b to the 1, and then we have b to the 2, b squared. So if we simplify that, 2, 0, that is the first If we just draw the Pascal's triangle 1, 1, 1, 1, 2, 1. So this is 2, 0. So 1, so a squared. And 2, 1 is 2. Even if you solve that using the formula, you will get 2, 2ab plus, 2, 2 is 1. So b squared. So if we do a plus b cubed, we get 3, 0, and then we get a cubed, and b to the 0, wala pang b, plus 3, 1, a squared, nagkagamay ang a, and then b appears, plus 3, 2. That's the third element in the third row of the Pascal's triangle, or the second diagonal. A b squared plus, and the final element, the third, where the third row and the third diagonal intersects, a to the 0, b cubed. And if we just complete the diagonal 1, 3, 3, 1, so 1 a cubed plus 3 a squared b, plus 3, 2 is 3 ab squared, and 3, 3 is 1 plus b cubed. So the Pascal's triangle is a feature of the binomial theorem, as well as the binomial theorem also features combinations. So that's very fascinating. Okay. So another application is finding the subsets. And in fact, in finding the subsets, we utilize the binomial theorem. So how does that work? So, well, when finding subsets, what the method that we really need to do is to list down, like to add all subsets, no? So the total number of subsets actually is the number of subsets for 5 choose 0. Well, 5 choose 0 is 0. I mean, it's 1. I mean, it's the 0th set. So the empty set, but the empty set is a part of the main set. So it's a subset of the main set. So we include that. And 5, 1 is with choosing 1 at a time. So the another subset in this main set is when we choose one element at a time. So how many subsets are there containing one element? And 5, 2 is 5 choose 2 is how many subsets are there, or how many combinations are there when you choose 2 from the 5 elements in the main subset. And 5, 3, how many subsets are there if we choose 3? Plus 5, 4, how many subsets are there if we choose 4? And plus 5, 5, how many if we choose 5? So this is the long version of the solution. But with the help of the binomial theorem, we can derive a formula. Now notice that this looks like the coefficients of a plus b raised to the 5, right? So let's utilize that. No, we have binomial a plus b raised to the 5, and these are the coefficients, diba? And this is what I'm talking about. So instead of carrying out the arithmetic in evaluating the combinations, we just note that 5, 0, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, they are the coefficients of the binomial a plus b raised to the 5. Now, if you expand a plus b raised to the 5, we get the expression in the right-hand side of the equation. We have a to 5, 0, a to the 5th, 5 choose 1, a 4 b plus 5 choose 2a cubed b squared, and so on and so forth. And to simplify this, no, to isolate 50, 51, 52, 53, 54, 55, we can let a equals 1 and b equals 1. And if we do that, a plus b becomes 1 plus 1, and a to the fifth becomes 1 to the fifth. A fourth b becomes 1 to the fourth times 1. But all of this just equal to 1, right? 1 to the fifth is equal to 1. 1 raised to the 4 times 1 is equal to 1. So notice that for all these coefficients and all these combinations are all multiplied by 1. So we can essentially just remove the ones, which is what we do when the coefficient, when any number is multiplied by 1. So wala na tanan. What's left is kani 5051 plus 52 plus 53 plus 54 plus 55, which is the original problem in the first place. And we find that that's equal to 2 to the fifth. And if we evaluate 2 to the fifth, that is equal to 32. So we see that there are 2 to the fifth equals 32 subsets of a set containing 5 elements. And we have actually derived the formula. So given a set, if we want to count how many subsets there are, we just evaluate 2 raised to the n, where n is the number of elements in the set. So we don't have to solve all of these combinations. No, all we have to do is 2 raised to the 5, where 5 is the number of elements. Or if there are 6 elements, 2 raised to the 6. So a set of n distinct elements has 2 to the n subsets. So we were able to derive this from the binomial theorem, which we find to be, it has features of combinations that are related to the Pascal triangle. So it all fits perfectly together. So again, if you're faced with a question, how many subsets are there for a set containing 10 elements? For example, we just say 2 to the 10, and that's equal to 1024 subsets. Instead of going over 10 to the 0, 10 choose 0, plus 10 choose 1, plus 10 choose 2, plus 10 choose 3, plus 10 choose 4, etc., etc. We just use the formula. And that's about it. That's the end of our lecture, and I hope you learned something today. And how do I stop recording?